Major technical advances in directional drilling began in the 1970s, when downhole drilling motors became common. These motors, which are driven by the hydraulic power of drilling mud circulated down the drill string, allowed the drill bit to be rotated on the bottom of the hole, while most of the drill pipe was held stationary. A piece of bent pipe between the stationary drill pipe and the top of the motor allowed the direction of the well bore to be changed. This, coupled with the development of MWD, facilitated the practice of horizontal drilling. MWD is using mud pulse telemetry that allows tools downhole to send directional data back to the surface without disturbing drilling operations. There are many reasons to drill wells horizontally. Increase the exposed wellbore length through the productive reservoir. Facilitate drilling into the reservoir where vertical access is difficult or not possible. For instance, producing reservoir rock that is positioned under a town or lake. Allow more wellheads to be grouped together on one surface location, called a pad, which facilitates a lower environmental footprint, reduces rig moves, and makes it easier and less expensive to complete and produce the wells. Whereas 20 years ago, wells drilled at 60-degree angles through the reservoir were achieved, horizontal drilling is now a normal practice. The process begins with the drilling rig arriving after a pad is prepared on about 2 acres of land. The actual drilling starts with a deep vertical path, extending thousands of feet below the Earth's surface. This step continues around the clock to maintain the integrity of the wellbore, or hole, and provide pressure control and solids removal during the process by circulating drilling mud. A rig is typically in place for about 3 weeks to drill a single well. Directional tools are then added to the drill pipe, and the path of the wellbore makes a smooth turn, tunneling horizontally into the targeted formation at depths ranging 3 to 11,000 feet below the surface. In the deeper wells, where hole stability and downhole pressures require it, the drill string and directional tools are then removed from the bore and steel casing is run to the bottom of the hole. Cement is pumped in to support the casing and to create a barrier between the various layers of exposed formation. The casing and cement provides the structural support needed to drill even farther into the shale formation without compromising the wellbore and drilling operations. Again, the drill string and directional tools are removed and cement is pumped in to support the casing and isolate the exposed reservoir sections in preparation for hydraulic stimulation treatments. Hydraulic fracturing, as used today in the oil and gas industry, was first developed in the U.S. in 1948. It was first used commercially in 1949. And because of its success in increasing production, was quickly adopted. Hydraulic fracturing is a method used to create fractures that extend from the wellbore into rock formations, which are typically maintained by a proppant. The method is informally called fracking. The technique is used to increase the rate at which fluids, such as oil, gas, or water, can be produced from the formation. By creating fractures, the surface area of the formation exposed to the borehole is increased, and the fracture provides a conductive path connecting the reservoir to the well, effectively increasing the rate that fluids can be produced from the reservoir. To begin the completion process, a series of perforating guns are lowered into the casing by tubing. These guns contain several shaped explosive charges, which are used to perforate a path from the casing to the reservoir. Once the perforations are completed, the perforating guns and tubing are removed from the wellbore in preparation for fracking. A hydraulic fracture is formed by pumping a fracturing fluid into the wellbore at a rate sufficient to increase the pressure downhole to a value in excess of the fracture gradient of the formation rock. The pressure then causes the formation to crack, which allows the fracturing fluid to enter and extend the crack further into the formation. In order to keep this fracture open after injection stops, a solid proppant is added to the fracturing fluid. Various types of proppants are used, including sand, resin-coated sand, and man-made ceramics, depending on the type of permeability or grain strength needed. The fracturing fluid can be any number of fluids, ranging from water to gels, foams, nitrogen, or carbon dioxide. In most shale plays, water with a friction reducer is the most common frac fluid utilized today. Once this process is completed, a plug and new set of perforating guns are pumped down the hole, which isolates the previously fracked interval and prepares the new interval for subsequent fracks. Horizontal wells are typically staged in 500-foot intervals, with a total of 6 to 10 repeating stages performed for each well. Once all stages have been treated, a bit and tubing are typically run into the wellbore, which drill out all of the plugs and are then removed. The well is then transitioned from completion operations to production. The hydraulic fracturing process typically takes place over 3 to 5 days per well and is widely credited with cracking the code for gas production in shale formations across the U.S.